Thank you for everyone joining today's section. So today we will discuss about the exterior lighting design analysis and optimization for the automotive industry. So here is the agenda today. So we will start from the introduction to the Ansys and the SPEOS. And later on, we will discuss the main component for this automotive design. So which is the optical part design, OPD, and the direct optimization in the SPEOS, and the Humanvision for the analysis. And also we have the SPEOS library and the standard measurement can be applied to make the analysis in the simulation. So let's start with the introduction to the Ansys and SPEOS. So Ansys simulation platform, we enable the digital transformation. So we cover a lot of the physics. So all this multi-physics, we can interoperate to each one. So today we will focus on the optical only. So in the optical, we have a photonic and the optics. So for the photonic, we use the numerical. Most of the case study will be the wave property of the light. So the wave propagation inside the waveguide. So for the simulation about the light property, which is the ray propagation, so we will done this analysis in the Zemax and the SPEOS. So in Zemax, we will done the design in the sequential mode. And for the system level, we will go to the SPEOS to simulate the reality. So here is the multi-physics potential for the full optics portfolio in Ansys. So we can design the component in photonic, and then we go to the level for the optical component, which is the lenses. And last, we can combine the component in photonic, the chip level, and the lens in Zemax into the SPEOS to simulate the real condition, which is include the 3D environment and also the lighting and human vision. So here is the interoperation for the Ansys optics portfolio. So just now I mentioned the image sensor we can design in the numerical. So all here is the parameter we will analyze in this numerical. And we also can make the lenses in the Zemax, and the parameter we can analyze in the Zemax. And after that, we combine these two information into the SPEOS and import the 3D and the environment. And we make the system level integration and analyze the entire system. So today we will focus on the SPEOS. So we will discuss the system level simulation and the validation. So first is the overview, what is the SPEOS. So SPEOS is an Ansys optical solution. So it can be used for ray tracing and making the photometric and radiometric analysis. And we also having the sensor, like the camera sensor, LiDAR sensor, and the human eye sensor. So we can use this sensor to analyze the real situation on the system level. Also, we cover the multi-physics compatible and also the cloud computing for the large simulation file. And here is the workflow for the SPEOS simulation. First, we will import our CAD geometry. Later, we will apply the material for all the CAD. After that, we will apply the light source into the source, and Next, we will input the sensor, optical sensor. After that, we can run the simulation in ray tracing mode and can be in inverse or direct simulation. So finally, we will get the result. Then we can analyze the photometric data, the radiometric data, colorimetric, or the spectral data. Here is some example application we will use for the analysis. So first is the photometric and radiometric study. We can use a radiant sensor, the irradiance sensor, and the intensity sensor to get the result for the photometric and radiometric study. And second application is the human eye and virtual reality. So this is the immersive and the observer. So we can use the VR sensor and also the human eye sensor to create this kind of study. So now we will go into the main part. So first is the optical part design. So in the optical part design, when we have a basic license, so we will have the parabolic surface and two volume. So for all the licensing, they have these three feature, one surface and two volume. So the parabolic surface, TIR lens, and the projection lens. So here is some sample photo for the illustration. And next, if we go to the advanced OPD, which is the Premier Enterprise license, we will have the poly ellipsoidal reflector and the optical surface at the bottom here. And also we have a volume like the optical lens. And next page we have a light guide and a freeform volume. So go to the next is the direct optimization in the SPEOS. So here we use a simple example, which is a prism. And also we have an incident angle. We want to find a smaller deviation angle between this region. So we start with this 60-degree incident angle. And finally, we will use the optimization to find the minimum deviation angle. And this is the final result we need to adjust based on the Direct Explorer workbench. So the optimization will be done in this, we call it Direct Explorer workbench. So first we will import the drag and drop the SPEOS. After that, we will import the geometry. So later on in the simulation task, we will import also the parameter. So first step, we will have this geometry, the simulation parameter, and we have this loop for the part A. So for the part B, we will add in the direct optimization. So the setting for the optimization will be here we have a result which is read from the sensor, and then the result is our target. So the variable is our incident angle here. So we will set the incident angle range from 30 to 70, and then based on the result, we will target on the minimum 40 flux on the surface. So here is the optimization result. We have a 10 step, and then we have a green color here, the highlight, which is the optimized result. And here is a graph view for the analysis. So there is 10 steps of the simulation and 10 incident angle and what is their output. So based on the chart, this is a function, the deviation angle as function of the incident angle. So we want to find the minimum deviation angle. So here is about 37.15 degree for the best optimization point. So next is the Humanvision. So Humanvision, we can get the result, the SMP result from the radiant sensor. Second, we can get from the human eye sensor. So after our simulation, we will use the virtual human vision lab to view the result, and we can apply all the human eyes feature into the simulation for the analysis. So here is the general idea how the human vision work. So they convert the spectral radiant. First is into the luminance. Second is the chromatic coordinate. So the analysis, the vision mode will be the scotopic and the mesopic, and also the photopic. So here is some of the parameter setting inside the vision. So first is the observer luminance, the surrounding condition. And second, we will set the age of the human eye. And also if the human have a color deficiency, we also can set here. And third is the parameter. We will set like the depth of field, the visual acuity, the gray effect, and also the vision mode evaluation. So here is some sample regarding the parameter in the human vision, like depth of field and the visual acuity, and also the gray effect. So others menu inside the human vision will be the measure and the virtualizing controller. So all these later on will demo in the simulation tools, the SPEOS. So next is the standard measurement. So we can apply the XML template into the sensor. So when the sensor finish the simulation, we can get the result with a measurement and also the rules. Then we can direct check the measurement point is pass or fail again the standard. So we also can get the measurement point here. What is the value for the particular region? And also we can isolate the result for different kind of analysis. So here is the standard. Either the XML template we can download from the SPEOS library, which is from the download center of Ansys, or we can use the photometric lab viewer. After that, we key in our measurement point and we export it as a template, so we can use it for future. Okay. So here is one of the sample of the measurement. So we have measure tools here, and we set all the point, and we set the rules name, and also what is the target value. So the measure tools will show either the measurement result, the simulation result is pass or fail from again the standard. So last is the SPEOS library. So our library will cover the light source and also the standard and also the optical properties like the material library, and also the here is the standard. So here is the download center, which is download in this page, the add-on package, and the optical library. So after download this zip file, we can extract it. So we will get all this information. And just now the XML library will be from here is the measurement standard. So we can import into the sensor, import in the template into the measurement, or we direct import into the sensor. So after the simulation, we will get this kind of result. Okay. So I will continue with the software. Okay. So this is the SPEOS software. So the software basically is using the space clamp for the drawing. So we have a sketch and a design. So the light simulation will be in this section. So we also follow the workflow. So first is the optical property for the material of the 3D CAD. After that, we have a source, and then we need to put in a sensor. And finally, we do the simulation. And also we can use the tools to view the result or edit the material. Okay. So here's the basic OPD is the example for the OPD's demo. Okay. So first is the parabolic reflector. So I already pre-built the model here. So this curve is built by the OPD, so which is in here. So we click on this, and the parabolic surface will be added into here, and we double click this surface. Then we can set the axis and the orientation, the position, and then we set the size and also the focal length, and then the OPD will auto form this surface. So behind we have a square surface. So this surface we will use this. Okay. Select this and we cut the surface. Okay, so here is the final surface we get. So we can do the reflector in this way. Just now the slide, we can do the reflector in the pieces and the desired shape. So we can using this combine and split tools to make the surface from different kind of shape. So this is the first one. And next one is the example for the TIR. So TIR is the same thing. We also use the OPD here. Now we click on this TIR lens. After that, we double click on this TIR surface, the volume, and then we need to put in the orientation and the position. After that, we need to set all the sizing on the TIR. So finally, the OPD module will auto-generate this kind of TIR lenses. Okay. So go to the next. So next is projection light. So projection light also the same thing. So we also use, this is the projector lens. So we also click on this and we get this projection lens. And same, we need to set the focus point and the optical axis, which is the orientation of this lens. And also we need to set the parameter, the size, and the focus, back focus length for these lenses. And next, we will go to the polyellipsoidal lenses, which is behind this one, the button here, which is a reflector on the LED. So the LED output from this plane and go out to the reflector and reflect to the other area. So this lens also, we click on this OPD and we create one polyellipsoidal reflector surface. After that, we will double click on this ellipsoidal surface. We have a same procedure, same workflow. We always set the orientation of the surface or the volume. After that, we need to set the dimension and also the focal length for the surface. So the OPD will auto generate this kind of surface of volume. So here we also input, like we put in the material for each the modeling, the cap here, and we put in the sensor. Okay, so last we need to put in the simulation, which is a direct simulation, and we can check the result here. So we will go to the next one, is the light guide. So light guide also using the optical part. We will use this button to create the light guide. So now we have a first light guide here. So it's the same. We also create the light guide from the orientation definition. After that, we need to define the body and the prism of the light guide. So after we declare all the information here, so we can press this button to generate the light guide. Okay. By the way, we are waiting. So we were talking about the light guide simulation. So the light guide simulation will be in three different mode. First is we have a profile with a line. So the light guide will be generated according to the line curve here, and we can generate the light guide in this way. And second type, we will go to a surface. So we have a surface, and then we have a line cut on the surface, and we also having a profile here. So after the simulation, we will using this surface, and we create the light guide based on this surface. So okay, so here is the output. We have a surface, and then we cut the surface perpendicularly, and we use a profile shape and follow the light here, the line, to create a light guide. So it's all in the Automate. And finally, we have the type, the last type of the light guide. So here, basically, we start with two lines. After that, we use pull tools. We use the pull tools to pull the line into a surface. So these two lines, we use a pull tools. Use these tools, and then we pull it into two surface, like this way. After that, we will draw the profile here, and we put in this region, and we set up the light guide parameter. Then after we do this computation, the light guide will follow this line to build the light guide. So this is from line, we create a surface, then we cut the unneeded surface region, and we create a profile and set all the light guide parameter that will follow the path we create and generate the light guide. So okay, so here is the output. So as we can see, here is a light guide part. Then we can close all the surface. So this is a light guide we generated based on the shape we created. So that will follow our line path and create the light guide in the particular way. So here is first is the OPD sample for the demonstration. So second is the optimization. So here is a sample file. We have a prism in this way, and the intensity sensor over here. And then we will measure the result here, just like just now I mentioned. Okay, so here is the measure tools, the result. So here is the incident angle. We have 60 degree, and then based on this result, the result is the deviation angle and the candela. So we will analyze the smaller deviation angle based on the incident angle, because this prism is using the refractive index 1.5. So the light will be reflected in different direction. So now our optimization want to design with which incident angle can get a smaller deviation angle. So we will base on this measurement result and put into the optimization tools, and we do the optimization. So here is the optimization tools. First, we will drop this SPEOS into here, and then we create a SPEOS workbench for the optimization. And second, we need to edit the geometry. So after we open, there is a click and the space clamp will be opened up and the geometry will be put in here. And next we will go to this, we generate the parameter. So the parameter will come out with one loop here. Okay, so after that, we will drag and drop this direct optimization into this section B. So we can double click on the direct optimization. So we will go to here. So now from here, this is the result we simulate inside the intensity sensor. So we have a target about minimum is 640, 40 minimum. And then this is our incident angle. So we can accept the incident angle from 30 to 70 degree. So based on this, we make the optimization in 10 steps. Okay. So we will set the optimization, the setting here for the step. And we will get the result on the chart after the 10 step run. So here is the result in the table form and the result in the graph chart. Okay, and just now we also show this in the PPT. So the green point is the verification and candidate point. So based on the optimization, we will focus on these 3 points will be the candidate to get a minimum deviation angle from the incident angle. So optimization will be up to here. So last is the Humanvision. So here is Humanvision tools. We can open from this light simulation, the viewer, and we can get the virtual human vision lab. So we will get this windows. And now we open the sample. So this is a headlamp design. So just now we have a measure tools and the virtual lighting controller, which is a special feature. So here we can measure the standard according to the standard measurement. And this we will show on this virtual controller first. So I already preset the light, because when during the simulation, we need to make the layer according to the source. So after the simulation, we can manipulate the source is on, either the source is on or off. So for example, we have a day. Okay, so here is a controller. We already set up when daytime and the nighttime, what is the effect. So we can adjust the lighting power in ratio or power mode, and we can click on this to turn it off or turn it on. So we can see the result on here by switching the configuration. Okay, so during a night view, we will see in this way. And maybe during the daytime, we will see the effect in this way when we open this light at the daytime. So, okay. Here we switch on all. And just now, we also have a Humanvision parameter control. So first is a condition for the observer. And second is the age of the human eyes. So if we change the age to maybe 60, then you will see like a little bit blur on the effect on a 60 years eye. Okay. And here bottom here is the color deficiency. So when we change the color deficiency, then we will see the colorblind person, what they will see in the actual. So here is a blue yellow. Then this kind of eye, they will see the light in the red color. And last is the simulation, like the gray effect. So when we switch the gray effect, they were different. And also we can switch off, then we can see we cannot see the effect at the night. So when we switch on, the thing will be in the night mode. And this virtual acuity is depend on the luminance. So in different luminance value, then we can see the things in different way, like the thing become blur or focus. So here is the effect for the virtual acuity. And lastly is depth of view. Okay, so here is a Humanvision demonstration. And lastly is the measurement. Okay, so this is measurement from just now the OPD demo. So we can use these measure tools, and then we can set the point with different kind of shape measurement, and we can set the precision and the size of the measurement, and we want to see the result in maximum, minimum, average, or anything. And here is the value based on our selected region. And here is the rules name. Okay, so when we set 350 as the maximum requirement for this point, so if our measurement is about here 23, so which is lower than the maximum, So it is passed. So it will show the green indicator. So for example, if like this point, we have a minimum 65 candela, but the measurement is about 35, and the system will show you fail. So they were highlighted in the red for this particular point. And also we can select all these, and after we select all these, the point will show on this simulation region. So we can actually see which point in which region and what is the point we are measuring. So this is measure tools, and we also can import and export the template. So if we don't have the standard, we can create our own measurement point based on the regulation standard, and we export it as a template. So for next time after the simulation, we want to do the analysis. So we can export and save it into the XML file. So after that, we also can use back it. We select back the XML file, also the XML file, and then that will show us the same measurement point as you save here. So all this is my presentation on today.